Welcome, everybody. Thank you for joining this webinar. Today, I'm moderating this very interesting webinar. We have with us three key companies from the silicon photonics value chain: OpenLight, Luceda, and Spark. And these three companies will introduce their key tools and workflows so that we can learn how to successfully design a 400G optical transceiver from initial idea to layout, implementation, verification, and tape-out preparation. We have three speakers today. Let's look at the schedule. The first speaker will be Shin, who is Director of Design Enablement at OpenLight Photonics. OpenLight provides design services and IP on power semis foundry process, and Jay will introduce you to their PASIC platform and how you can tape out with them. After Jay, we are going to hear from Aysan Anamoradi. She is Application Engineer at Luceda. Luceda is a leading provider of peak design software. So after hearing from Jay what OpenLight offers as a fabrication platform, Aysan will show you how you can design to be able to tape out on a platform such as OpenLight. So she will guide you through the design and verification of an optical transceiver, going from schematic creation in IPKISS Canvas through complete circuit design, showing how you can perform functional verification and prepare it for a successful tape-out. We are then going to close with Aeon Williams. She is Software Application Engineer at Spark Photonics. Spark provides design services and DRC software and is a distribution partner of Luceda in North America. And Aeon will demonstrate the design rule check process so that you can make sure your designs adhere to foundry design rules. So that you can do DRC checks using the Luceda Link for Check Mate DRC, ensuring compliance using Spark's Check Mate DRC tool. This is a webinar where we're going to have a Q&A session at the end, so I strongly recommend to ask questions in the chat so we have the chance of asking our speakers all the questions you've been thinking about in the build-up to this webinar. So feel free to ask questions in the chat or unmute yourself at the end and ask questions directly. If you write them in the chat, I will be happy to ask the questions for you to the speakers. This being said, I will give the virtual mic to Jay Shin. The floor is yours, Jay. You can share your screen.
Okay. Thank you very much, Chiara, for the introduction. Let me see if I can share my screen. Just a moment. Okay. What is it? Can you see my screen okay?
I can see it.
Okay, perfect. So why don't we get started? Let me just see. So, hello, everyone. Thank you for joining the webinar. Today, I'd like to provide you an overview of what OpenLight Photonics offers to our customers, and also the PH18DA technology we have developed in collaboration with Tower Semiconductor. Okay, why does this not move? Okay, there you go. First, I would like to provide an overview of how 3.5 material is integrated into the process to deliver active devices such as lasers, modulators, and photodetectors at wafer scale. So the first step in the process is the pre-bond process, where silicon and nitride devices and waveguides are etched into the wafer. The next step is to bond known good 3.5 material only where they are needed. So these are shown as these red and green bars in the second figure here, right over here. So then the next step is what's called the substrate removal step that leaves just the epitaxial layer needed to form the active devices. So you can see here the thickness of these bars have thinned quite a bit. After that is the 3.5 processing, and this is where the remaining material on the wafers is patterned to form diodes. The important thing I'd like to highlight here is alignment between the 3.5 portion of the device and the silicon layers underneath are defined by lithography, which has sub-micron accuracy. So this eliminates any performance variance due to misalignment, and that is a big advantage of our platform. Finally, metallization is performed and the chips are hermetically sealed by the passivation step. So what are the value proposition of PH18DA? So there's multiple vectors, so I'll go into each of them. In terms of performance, the PH18DA platform has low waveguide routing loss on the order of about 0.3 dB per centimeter for silicon waveguides and 0.2 dB per centimeters for nitride waveguides. For the active devices such as lasers, they have better than 90% coupling efficiency into the silicon waveguides. Compared to externally coupled lasers, depending on the technology, I think it's anywhere between 1 to 1.5 dB coupling loss. Also, our electroabsorption modulators require lower voltage swing compared to silicon modulators to achieve the same level of extinction ratio. So when it comes to reliability, lasers are more reliable compared to external lasers for multiple reasons. So first, they're hermetically sealed, so less susceptible to damp-heat failure. They also are able to operate at a lower current density due to the lower coupling loss into the circuit, so you don't have to drive them as hard to get the same level of power in the circuit. And finally, they do not have edge facets, which could result in, optical mirror damage that leads to failure of the laser diodes. Also, having fewer assembly steps improves reliability. For example, there's no need to attach 8 external lasers for a 2x FR4 PIC. Our platform can also reduce cost and increase operational efficiency by simplifying the supply chain and eliminating margin stack up. Also, eliminating the steps necessary for assembling lasers into a package can significantly lower both CapEx and OpEx. And since these lasers and SOAs are integrated to the wafer, scaling PICs to higher channel counts is straightforward and does not require customers to invest exponentially in CapEx or OpEx, which we believe is a huge advantage. So both multi-project wafer prototype runs and production runs are available through Tower Semiconductor for the PH18DA platform. When it comes to the PDK, fully validated PDKs are available for multiple EDA tools, including Luceda IPKISS and Synopsys Optical Compiler. These PDKs include both O-band and C-band devices, which are suitable for a wide range of applications such as datacom, AI, FMCW LiDAR, and more. The passive devices include the general components that's available, so waveguides, splitters, filters, and optical I/O. The active devices include tunable lasers, DFB lasers, SOAs, high-speed EAMs and photodiodes, and finally, low-speed monitor photodiodes. Our lasers, modulators, and photodetectors have completed GR468 qual. So on the bottom right is shown an example of the laser drive current, and it's stable over 5,000 hours of HAL with 0 failures. Here we show some of the performance figures of our heterogeneously integrated DFB laser and SOA. Just a moment, sorry. Can you still see the screen?
Yes, we can still see the screen, yeah.
Okay, sorry. Okay, so I'm sorry. Let's move on. So one big advantage of the DFE lasers over the tunable lasers is that it greatly simplifies control. The DFE grating is etched in silicon, which enables targeting multiple wavelengths and allows for novel design. Our DFVs have very, very efficient tapers, as I mentioned before, over 90% efficiency, coupling, light from the 3.5 material that provides gain to the low-loss silicon waveguides used for routing. Our SOAs are available for both O and C band. They have low noise figure due to efficient coupling into waveguides and can deliver up to 20 dBm of output power. This makes them attractive for both datacom and LiDAR applications. Okay, here we show the performance of our 200G electroabsorption modulator. This modulator has been designed for DSPs using standard EML drivers. We've also demonstrated interop of our modulators with a commercially available DSP and driver. Using 224G PAM4 signaling and single-ended drive voltage of 1.4 volts, we're able to measure T-Q around 1.6 dB, which I believe is a pretty good number at 200 gigahertz. So looking beyond 200G, earlier this year, in collaboration with Rigas University and Keysight Technologies, we've demonstrated the ability to transmit at data rates close to 400 gigabits per second by using different modulating schemes on the same 200G modulator that I just showed. We have also demonstrated 340 gigabits per second data rates with PAM4 modulation, and development is currently in progress to further increase this data rate to 400G. OpenLight Photonics also has reference PIC designs available for 800G and 1.6T, suitable for datacom and AI ML applications. Customers can leverage these designs, which have been tested and validated in silicon at the PIC level, to accelerate their time to revenue. We also have starter kits, layout artwork, and design files for these reference PICs, which are available on request. And later on, from Luceda Photonics, you'll see implementation of how you can lay out, the 400G section of the 2xFR4 PIC. To summarize, the PH18DA technology made available through Tower Semiconductor offers a high-performance, scalable, and cost-effective platform customers can design into for a wide variety of applications. The main active components, such as the laser, modulator, have completed GR468 qualification. The platform also provides a path for architectures with data rates beyond 200G per lane. OpenLight also offers reference designs for 800G and 1.6T PICs, which customers can leverage to accelerate time to market. We also provide a wide range of services for customers, including design, layout, wafer lot management, testing, and back-end services. For more information, please contact OpenLight Photonics at info@OpenLight Photonics. Thank you.
Thank you so much, Jay, for the nice presentation. We can now go to Aysan, who is going to show us how we can leverage the Luceda Photonics design platform to design with the OpenLight PDK.
Hello. Thank you.
Sorry, before we switch topic, I just said is Marco Lamponi here from Nubis Communication.
Hi, Marco.
Hi, I had a question on the yield of the individual components on this platform, and how this impact the yield of the final module, especially when you go to a high number of channels. For example, on a DR8 transceiver, where you have 8 laser, 8 modulator, number of monitor photodiode, and 8 high-speed photodiode. So, which kind of yield are you able to obtain?
So hi, Marco, this is Steve Alliston from OpenLight. Just to answer your question. So typically on the device level, we measure yields in the high 90% on the device level. And that translates to a pretty usable yield when you are combining, as you say, large quantities of devices onto a single PIC.
But if you say you mean I90 or 90? Because 90
High 90s. Sorry,
High-
beg your pardon. High 90s.
I see. Okay. And I had another question on the TDQ of your 200G modulator. In the presentation, you mentioned 1.5, but in the graph, I think I was seeing 4.5 TDQ.
I think that was probably the extinction ratio before deconvolving some of the cables. There's multiple eyes presented in that.
But so when you refer to the TDQ of your module, of your transmitter, you typically obtain 1.5.
Certainly, yes. In this, which was done with EVKs with cabling, we were able to achieve a good both TDQ and extinction ratio, despite the challenges of working through over 12 dB of RF losses at the Nyquist frequency.
Okay, but so you don't have like data with some kind of driver, commercially available driver, or flip chip driver, or wire bonded driver.
So both of the components we used were commercially available from both MACOM and Marvell. So it's the Marvell Nova DSP and the MACOM driver.
Okay, thank you very much.
My pleasure.
Thank you, Marco, for your questions, and Steve for answering. The floor is yours, Aysan, now to go through the design flow.
Thank you, Chiara. Okay. Okay. Hello, everyone, and welcome. I am Aysan, and I'll guide you through this part on designing and verifying 400G optical transceivers using Luceda software. First, I will give you a short introduction to Luceda platform. Luceda Photonics was founded 10 years ago out of the Belgian photonics ecosystem. It was created with the long-term goal of enabling photonics IC designers to enjoy the same first-time right experience as electronic IC designers. Our mission is to accelerate the time to market of PIC design teams by helping them set up a flexible and efficient design flow. We have a presence around the world, including a branch office in Shanghai. We have partnership with Spark Photonics in North America. And we also have resellers in Taiwan and Tokyo. By using Luceda, you will have access to a team of photonics experts who can help you achieve your goals. We aim to achieve our goals through the Luceda Photonics design platform, a Python-driven design platform that leverages the flexibility and automation of code to take you from component design and to circuit design and simulation and design validation all in one place. Our core product, Luceda IPKISS, consists of all the core features of the photonics design flow, from schematic capture to circuit layout and simulation, and also component layout and simulation and design verification. You can access PDKs for many different foundries across material platforms, as well as design kits for assembly and testing. We also offer specialized modules such as AWG Designer and IP Manager to help companies to validate and test their IP libraries. And also we offer integration with third-party tools, including device and system simulation tools such as the newly released Link for OptiSystem, and also a Link for TiD3D, Link for Siemens EDA Edit, and Check Mate DRC. So as you know, the goal of this webinar is to showcase the design process of an application that is an optical transceiver. Using Luceda PDK for OpenLight, the circuit is designed in IPKISS, and Luceda Link for Check Mate DRC can be used at any stage during the design to make sure that the violations are spotted as they are defined. And once the design is DRC-clean, it can be taped out to foundry for fabrication. I would like to show you how to go through the design flow in IPKISS by telling you the story of Eva. Eva is a highly skilled photonics engineer and designs photonic integrated circuits for transceivers. And she has an idea for their new project that is designing an optical transceiver by using OpenLight PDK. Her journey begins with creating a schematic capture in Canvas, and then she moves on to designing the layout in IPKISS. And finally, she uses the tools in IPKISS and also Canvas to verify the circuit and prepares her design for tape-out. So she gathers her team and tells them that she has a proposal for their next project. And her colleagues ask her about the idea, and she said that she can create a schematic of the circuit to show it to the team. Then Eva begins creating the schematic in IPKISS Canvas by using components from the OpenLight PDK. She arranges these components with a simple drag and drop method and connects their ports to define the circuit structure. And once the design is complete, then Eva explains how each part functions and interacts with other components within the circuit. So Eva's team likes the idea, and so she can kick off the design. To start the design, Eva considers starting with designing the transmitter part of the transceiver. And she's thinking of a 4-channel transmitter, which has plenty of active components that all of them need to be connected to several bond paths. But the problem is that when she thinks of defining all the bond paths at the top level, she finds the design hard to manage and track. And she thinks that it will be very chaotic. So she plans to break the whole project down into some steps, but needs some advice on the best way to do it. So she reaches out to Luceda's team for some guidance, and she knows they are there to help. And sure enough, they get back to her with some advice for organizing her design project and help her get started. The flow that they suggest is that she can start by building a library on top of the PDK. First, she can connect active components to bond paths, and it will help her keep the building blocks organized in a clear and structured way. Then she can use library components to design a higher level circuit. And also, again, she can use the single channel circuit to design the 4-channel circuit. So this way, she can design her circuit in a hierarchical way without making one design too complex. Another benefit of doing so is that she can use the library for further designs, for example, the receiver part of the transceiver. In this slide, there is a brief introduction to libraries in IPKISS. Libraries in IPKISS are built on top of the Foundry's PDK, which contains all the information about the fabrication processes and design rules provided by the Foundry. And typically, the companies that receive a PDK will develop their own libraries based on that PDK. And these libraries can contain simple to complex components and can be considered as the company's intellectual property. Also, these libraries can be reused in different projects, which can make the design process more efficient. Moreover, these designs can be combined with assembly or testing design kits, which are useful for the final integration, testing, and packaging of the design. So Eva now wants to create a library in IPKISS. It can be made by some folders containing some Python files. The library that she will make is based on the OpenLight PDK, so she sets the OpenLight technology for her library. Now she can start adding enriched components with the bond paths to her library. The PDK components that should be connected to bond paths are lasers, laser electro-absorption modulators, phase detectors, and switches. Here is the list of the library components. Let's take a look at the laser, for example. The laser at the top is a part of the OpenLight PDK, while this one is a custom component from the library, which is connected to the bond paths. Also, components within the library can also be used to design more complex components in the same library. For example, a simple component consisting of 2 connected bond paths can be used to design this laser in the library. Once the library components are defined, EVA can export the library that can be used in Canvas. EVA can then use these library components again to design schematics. And she also can assign symbols to each component based on its function. For example, she can assign a laser symbol to the laser component and MZI symbol to the MZI components. Now the library is set up. EVA can use it to design the single channel circuit. She can import it just like importing the PDK. To design the single channel circuit, she should take some steps. First, she must define all the instances for the circuit, such as, for example, these instances can be laser splitters and switches, and these can be either PDK components or library components. Next, she needs to specify the placement of each component. She can choose to place them independently or relative to other components. Then she should define the connections between the components. And thanks to IPKISS, the order of the placement and routing steps doesn't matter. IPKISS automatically takes care of putting everything together correctly. Let's take a closer look to the different steps. The instances can be defined one by one like this, or sometimes, for example, a circuit contains multiple copies of the same component. For example, this circuit needs at least 3 terminators to connect to unused ports. So instead of defining them each one by one and manually, EVA can use a for loop, and thanks to using the capabilities of Python in IPKISS with just 2 lines of code, she can create all the similar instances at once, and this will help to save time and make the code more efficient. Once the instances are defined, EVA can start placing them in the circuit. She can use i3.place to replace the laser or a port of it at 0, 0 coordinates, for example, and she can also flip components vertically or horizontally, or even rotate them by a specific angle. She can then place the electron absorption modulator or its port at a distance relative to the laser or its port. And finally, she can, for the unused ports, EVA can directly terminate them by joining them to a terminator. This way, no waveguide is generated between these 2 components. After placing all the components, EVA can connect the ports and set a specific bend radius for all the connections. For example, in this case, she is using a Manhattan connector, which creates 90-degree bends. However, EVA can also use other connectors available in IPKISS depending on the needs of her design. While connecting the components, EVA encounters an obstacle in the path of the connector that needs to be avoided. For example, the port of the coarse AMZI should be connected to the port of this phase detector, but this LV switch is on the way. So when defining this connection, EVA can specify that the connection should have a horizontal section that is 75 micrometer away from the bottom of the LV switch. By the way, oh, sorry. Yeah, we would like to invite you to our upcoming training on placement and routing features in IPKISS. Please visit our website for more information and for registration. Finally, EVA can export her design directly to a GDS format with the correct layers from the foundry PDK, or she can visualize it using IPKISS Visualizer. Before moving on to designing the 4-channel circuit, EVA can capture a schematic of her layout using Canvas and perform some verification steps in Canvas. The first step is to compare the exported schematic with the initial design. she can verify the interconnectivity between components and ensure everything is correctly linked. One difference that she notices is the generated blocks representing the waveguides between these components. And also from the exported schematic, the automatically generated transitions in the connections are visible. Moreover, she can also look at different properties of the connection. For example, she can easily find the band radius and length of the waveguide by going to its properties. She can also view various parameters of the components in her circuit. For example, on this card for the MMI, she can see details related to the layout properties. And it is also very easy to spot unconnected ports in Canvas. Eva notices, for example, this unconnected port on the MMI, and then she can decide whether it should be terminated or left unconnected to be linked to another component in a higher level circuit. Eva can run a DRC using Luceda Link for Check Mate DRC. In fact, it is recommended to do it at all levels of the design, as it allows the designer to address the errors as soon as they are made. I will continue the design, but Aeon from Spark will show you the process. Now Eva is ready to design a 4-channel circuit. She can follow the same steps as she used for the single-channel circuit, that is defining the instances, placing components, and making the connections. Because a 4-channel transmitter consists of 4 copies of the single-channel circuit, Eva can easily define 4 instances of the single-channel circuit using, again, a for loop. I won't go through the placement and routing specifications again for this circuit, but you can follow them in the example on the Luceda Academy. Also, by defining the design in a parametric way, it is possible to change those parameters when instantiating the circuit. For example, Eva can change the band radii over the whole circuit, or change components in the circuit by only one line of code. After finishing the circuit design, it's time to go through some verification steps again. And Eva now uses verify mean distance function to check the spacing between the ports and make sure it makes the foundry's requirements. She runs the function for the electrical ports in the 4-channel circuit, and she looks for any ports less than 150 micrometer apart. And also when she runs the function, this statement is printed, ports have enough distance between them, so she can go to the next step. Another issue that Eva can address before takeout is the acute angles. These angles may violate the design rules, and they should be patched. By using IPKISS tools, she can not only find these errors, but also she can fix them in the layout. Finally, Eva wants her outputs to be phase matched to improve the circuit's performance. For example, she needs to make these 2 waveguides equal in length and number of bands. She can export the full design to Canvas and check the length of the 2 connections as shown earlier. And then she can add some control points to the shorter connection and adjust their positions until both connections are equal in length and number of bands. It is also possible to do this process in the code automatically. So everything presented here is also available in the Luceda Academy website. You can also find the codes of this example in the Luceda Academy material, which is installed together on your with the Luceda software on your computer. And then you can run it if you have the OpenLight PDK. Now, starting from the schematic capture in Canvas, designing the circuit and verifying it in both Canvas and code environment, Eva can run the DRC again on the full circuit and send the design for fabrication. Thank you for your attention, and Aeon will, I think, demonstrate how this link works.
Thank you so much, Aysan. I see there are a couple of questions in the chat. If it's all right for everybody, I will keep them for the end during the Q&A session in the last 5 to 10 minutes. And I will now give the floor to Aeon, who can show us how to run DRC on your designs.
Thank you very much, Chiara. So hello, everybody. My name is Aeon Williams from Spark Photonics. Let me share my screen real quick and we can get started talking about Check Mate DRC, which is a design rule check solution for photonics layouts. So first of all, a little bit about Spark Photonics. So here at Spark, we have 3 lines of business. The first we have is technical services, including design and layout at leading photonics foundries in North America, Europe, and Asia, as well as PDK development and consulting. Second is software and hardware, where we are the exclusive North American agents for Luceda Photonics. We also produce Check Mate DRC, which I'll be showing you today. We sell PIT kits with already fabricated chips and measurement data for education, training, and calibration purposes. And we also have several education and outreach programs through our nonprofit Spark Photonics Foundation. All right, so introducing Check Mate DRC. This is a DRC solution designed to integrate into your photonics workflow from start to finish. Check Mate DRC can be accessed via a GUI interface or directly from Luceda IPKISS, with features designed to enable you to troubleshoot your layouts efficiently from concept to final verification. We offer reasonable pricing with a variety of licensing options, and I'm excited to show you a demo today of what we have. So here we have the Check Mate DRC graphical interface. Here we can see the different options that we can select, where we upload a GDS file. We choose which technology we would like to run. So today we're talking about the Tower Semiconductor PH18DA technology. We also have the option to select specific layers or rules so that while you are troubleshooting your layout, especially at the beginning stages, you don't necessarily want to run a full run on your layout. So you can select down which layers or rules that you would like to run specifically to focus on different parts of your layout and then run them all towards the end. So we also have the option to run Check Mate directly from IPKISS. And so this enables you to run DRC as soon as your layout is started being produced. And so I can actually show you what that looks like. If I open up PyCharm, here we have a very basic layout. It's not the layout that we saw being produced in our previous slide deck for simplicity and IP purposes. So here we have a very simple layout. And if I run this, we will see, first of all, a visual of what we will be running DRC on. So here we have 2 MMIs, and it looks like their ports are touching. But we'll see what the DRC is able to catch. And so it's run with a very simple command. So we create our layout here, we write it as a GDS file, and then we run DRC checkmate where we can feed several options. And so now here we have our MMI layout that we just created in IPKISS. And if I zoom in, we can see there's actually a gap between the ports where we expect them to be touching. And here we have the error that was caught by Check Mate DRC, and it's highlighting the part that has an issue. So here we can see, oh, our ports aren't touching. Okay, now we need to go back into IPKISS and fix this. And that is the basics of how we use Check Mate DRC. Check Mate DRC is available currently for Tower Semiconductor PH18DA and PH18M. We are also working on different foundries and technologies. And so for more information, please contact info@sparkphotonics.com, and we'd be happy to get you set up with a trial or answer any questions.
Thank you, Aeon, for the very nice presentation. We have a couple of questions in the chat. I see that Steve is busy answering. So let's start from the beginning. From Yuchun, the question was, what is the output power and Aeon values for a single channel from the 1.6 terabyte DR8 to FR4 PICs used in the reference design, for example, at 80 degrees? I see Steve has answered in the chat. Would you like to repeat your answer so that everybody can hear it?
Yeah, sure. So just for the oral audience. So all of the PICs are designed and tested against the applicable MSA or IEEE standard for the typical codes, and they are designed to work on cool between 0 and 80 C at the die temperature.
Perfect, thank you. We also have another couple of questions from Marco. What is the laser power injected in the EAM in order to obtain the 200G eye diagram? And have you tested the EAM versus burst error? What is the maximum laser power you can inject to avoid burst errors?
So I don't actually know the answers to that. I mean, this is a benchtop system using EBKs, more as a proof of concept than anything else. There is, of course, a limit to how much power you can inject into an EAM before you start to see catastrophic failure. But we've not seen that in practice on any of the devices that we've used so far.
All right, thank you. Now there is a question for Luceda from Mustafa. Is phase matching done on geometry basis, or does it also take into account the waveguides model? I can answer this one. In this case, the say path length matching was done on geometry basis, which is in most cases fine if if the cross sections of your waveguides are the same. Then of course, if the cross section changes or the materials change, then you will need to do phase matching. We have then see a question from James for Aeon. How does Check Mate DRC differ from K-Layout's inbuilt DRC tool?
Yeah, great question, James. Thank you for asking. I would say a few different features that we have. So we are more optimized in the sense that we can run more efficiently, so saving you some time. And we also have the options, like I was saying, to save you more time, reducing the number of rules and layers that you're running when you run DRC. Sometimes a full reticle layout, running DRC on that through K-Layout can take a lot of time and computing power when you'd rather be working on your layout or doing other things. And so having that option to run more smoothly, more quickly, as well as integrate directly into software such as IPKISS, where you can integrate that into your workflow so that your whole process is much more efficient with DRC.
Thank you, Ian. Are there any more questions?
Yeah, I have another question on the DRC check. So typically K-Layout, it works well for this kind of minimum size and the standard, let's say, easy DRC check. But when it comes, for example, on the check for the metal, when you have to have a certain width, minimum width, depending on the overall size of the metal, it's much more tricky to write down rules that are actually finding the errors correctly. So can you comment on that? And is your tool capable of performing this check efficiently?
Yes, I'm not entirely sure which rules you're referring to specifically.
I've been confused, but like when you have, for example, you have a minimum size for the metal, let's say it's alpha micron, and this is the minimum size for an isolated metal. But then if you have a line that is 20 micron and you are connected to that line, then the minimum feature size changes. So you basically have to put some condition to your rules. It's not a rule that is valid everywhere, but it depends on the surrounding.
Interesting. So I would say in general, we have the entire tower rule deck written and working, and so If we have that specific rule, I'm not sure off the top of my head, but we're
Not
able to
familiar with
catch, I would
how-
say,
I'm not
most
familiar
of the
with how
DRC
it is.
errors.
It may well be that this is not in there, so that's okay.
Okay. Okay. But I would say we're able to catch most of the DRC errors. And that sounds familiar to things that we have done. And if this is something that you're particularly struggling with, other DRC software catching, and you have a layout that has this, or you have a rule deck that goes over this, then we would be happy to talk to you and get something custom written for you, see what we can work with, to see about what we can do if we don't already have that in Checkmate. So we'd love to be in contact after this webinar to go over that.
Okay, thank you very much.
Thank you, Marco, and thank you, Ian. If there are any more questions, you have a bit of time to take a couple more. Maybe I have a question for Ian, also regarding DRC. So what is the biggest pain point you have encountered working with, Spark Photonics is a design house, so you do designs yourself, but you also work with other people doing designs. So what is the biggest pain point around DRC that you have encountered? And when do you think is the optimal time to run Checkmate during your design cycle?
I would say the biggest pain point for DRC is the fact that a lot of DRC is run at the end of your layout cycle, which also has tight timelines and deadlines with taping out with a foundry. And so we really advocate for starting your DRC process as soon as your layout starts. So that kind of answers both of your questions there. When is the optimal time to start DRC? I would say yesterday. And so being able to integrate it into your workflow pretty much from the get-go will save you a lot of time while you're working on your layout and towards that end when those deadlines get really tight. So yeah, thank you for asking.
Thank you for your answer. We have another question from Mustafa. Can Checkmate be called from CLI command line independent of other EDA?
So currently Checkmate can be ran through the GUI interface. So no matter what layout software you use, you can use it through that. And then we work through the IPKISS command line specifically. So if you'd like a trial of IPKISS and Checkmate to be able to see how those work together, we'd be happy to set that up.
Thank you. All right. If there are no more questions, I would like to thank all the speakers again. Thank you, Jay and Aysan and Aeon for your very nice talks. Of course, if you're interested in continuing conversation with either OpenLight, Luceda, or Spark, feel free to reach out to us. You can contact Luceda at info@lucedaphotonics.com, and we are happy to put you in contact with the Spark and OpenLight as needed. Other than that, thank you so much for joining us, and see you at our next webinar or online training.
Thank you.
Thank you very much.
Thank you all.